In this video, we will cover sections 7.1 to 7.4 in the textbook. These videos are meant to supplement your readings for class and additional classroom lectures with your instructors. I would advise using the provided Rmarkdown file to follow along with the video. We will focus on using both parametric and non-parametric methods to create confidence intervals for the true slope by hand and using R, and how to perform a hypothesis test for slope. In addition, we will work through an example from the textbook complete with interpretations and conclusions of statistical tests. A confidence interval gives us a range of plausible values for the parameter of interest. It can also give us information in regards to a hypothesis test. If the null value is included in the confidence interval, then there is no evidence against the null hypothesis, and the null value is a plausible value for the parameter of interest. However, if the null value is not included in the confidence interval, then there is evidence against the null hypothesis, and the null value is not a plausible value for the parameter of interest. The confidence interval is built around the estimate for our parameter, in this case, the estimated slope. To the estimate, we add and subtract the margin of error, the t-star multiplier, times the standard error of the estimate. The t-star multiplier used for confidence intervals for slope and the y-intercept comes from the t-distribution within our sample size minus 2 degrees of freedom. We will use R to find these multipliers. The standard error will be given in the R output for the linear model. This same process will be used to find the confidence interval for the y-intercept using our estimate for the y-intercept and the standard error of the y-intercept. Let's work through the blood alcohol content versus beers dataset. In this study, 16 students were randomly assigned to consume each number of beers. Let's look at the simple linear regression model for this dataset. First, we'll use the R output to identify the estimated line of regression. So remember, we get our estimates from the R output here. So the estimate for the intercept is negative 0.0127. The estimate for the slope is 0.018. The explanatory variable for this data is the number of beers, and the response variable is blood alcohol content measured in grams per deciliter. Using the values from the simple linear regression output, we find the line of regression. The estimated blood alcohol content is equal to negative 0.013 plus 0.018 times the number of beers. To interpret the slope coefficient, we'd say for each additional beer consumed, the expected blood alcohol content will increase on average by 0.018 grams per deciliter. The interpretation of the y-intercept says for 0 beers consumed, the expected blood alcohol content will be on average negative 0.13 grams per deciliter. Let's check the assumptions for a simple linear regression test. Both variables are quantitative, so the first assumption is met. Since there's only one measurement per student and their blood alcohol content should not affect another student, there is no evidence against independence. Looking at the scatter plot, we can see that there really is no evidence against linearity. We can also look at the residuals versus fitted plot, and we can see that there is no curved pattern in this either. Both show a linear relationship. Though there may be a possible outlier, using both the residuals versus fitted plot and the scale location plot, there is little evidence against constant variance. There is some evidence against normality. We have a possible right-skewed distribution in the residuals. When we think about influential points, we can see that there is evidence against the assumption of no influential points, because here we have that influential point with a Cook's distance of greater than 1. We're going to continue on finding the confidence intervals and looking at a test for slope. To find the 95% confidence interval, we will need the estimates for slope and the y-intercept, the t-star multiplier with n minus 2 degrees of freedom, and the standard error of each estimate. To find the t-star multiplier for a 95% confidence interval, we find the t-value at the 97.5th percentile from the t-distribution with n minus 2 or 14 degrees of freedom. This value is 2.145. Looking at the summary of the linear model, we can get the estimates for both slope and the y-intercept and the standard error of the estimates. So we already found our estimate for the y-intercept is negative 0.0127, and the standard errors are given in the next column. So the standard error for the y-intercept is 0.0126, and the standard error for the estimated slope is 0.0024. We can use R as a calculator to find both endpoints at the 95% confidence interval. Here we have our value of slope minus our t-star times the standard error of the slope. And that gives us a value for our lower value of 0.136. To calculate the upper value, we're also finding the estimate of our slope plus our t-star multiplier times the standard error of the slope. We can also use R to find the confidence interval for the slope, or the code confident of our linear model. This right here gives the 95% confidence interval for the y-intercept, while down here gives the 95% confidence interval for the slope. The 95% confidence interval for the true slope is 0.0128 to 0.0231. When we interpret the slope, we need to think about what slope measures. The slope shows the expected changes in y for each increase of 1 unit in x. When we interpret the confidence interval for the true slope, we look at how confident we are in the range of expected changes in y for each increase of 1 unit in x. For this confidence interval, our interpretation would read, for each additional 1 beer consumed, we are 95% confident that the true change in the mean blood alcohol content will be between 0.0136 and 0.0223 grams per deciliter. The entire interval is positive, so we are 95% confident the true slope between the number of beers consumed and the blood alcohol content is positive. Let's explore what this means in context of a hypothesis test. If there is no linear relationship between the explanatory and the response variable, we would expect the slope to be 0, or beta 1 is equal to 0. The alternative would test that there is a relationship between the variables. The test statistic used to test slope takes the value of our statistic, our estimated slope, divided by the standard error of the slope. We could also use a one-sided test, testing to see is there a positive linear relationship between x and y, looking at a right-sided test, or is there a negative linear relationship between x and y, looking at a left-sided test. To get one-tailed p-values, if our test statistic is greater than 0, for an alternative where we're looking at a positive linear relationship, or if our test statistic is less than 0 for a left-sided test, we would divide the two-sided p-value by 2. In our beers and blood alcohol content example, we assume that there is no linear relationship between number of beers drank and the blood alcohol level in the population. And we're testing the alternative that there is some linear relationship between number of beers drank and the blood alcohol level in the population. Let's go back to the R output to calculate the test statistic. So to find T, we're going to take the estimated slope, 0.018, divided by 0.0024. This gives us a test statistic of 7.5, which we can also see right here in our R output, 7.48. This is a large T value, and our P value is 2.97 times 10 to the negative 6, which tells us that our P value is less than 0.0001, a very small P value. Let's revisit the confidence interval. We saw that the entire interval was positive and did not include the null value of 0. So we can see that both the confidence interval and the p-value show evidence against the null hypothesis. Since this p-value is so small, we will consider it less than 0.0001. The p-value represents the probability of observing the sample result, or more extreme, under the assumption the null hypothesis is true. So our p-value shows that if there is no linear relationship between the number of beers drank and the blood alcohol content in the population, we would see a slope of 0.018 or farther from 0, with a probability less than 0.01%. A small p-value provides strong evidence against the null. So in conclusion, we find there is very strong evidence against the null hypothesis that there is no linear relationship between the number of beers consumed and the blood alcohol content in the population. This is based off a t-test statistic under a t-distribution with 14 degrees of freedom of 7.48 and a p-value of less than 0.0001. We can conclude that there is a linear relationship between the number of beers consumed and the blood alcohol content in the population. Let's see if we get similar results with non-parametric methods. When there's evidence against the normality assumption and there are no influential points, we can use parametric methods. To create the confidence interval, we will use bootstrapping methods, sampling with replacement from the original data to get an estimate of the sample-to-sample variability. To find the p-value using non-parametric methods, we will use permutations of the test statistic, the t-value, to create the null, our permutation distribution created under the assumption that the null is true. Let's return to R to see these results. First, we'll find the estimate of the slope and assign that to tops. To find the p-value from the permutation test, we're going to take 1,000 different permutations. Here's the code to find our p-value. We can see our p-value is essentially 0, less than 1 out of 1,000. Based off the permutation graphs, we can see that our test statistic falls way out in the tail of the distribution, showing no observations at the test statistic or more extreme. To find the 95% confidence interval using bootstrapping, we're going to sample with replacement from the original data. Here is our confidence interval for the true slope, 0.0124 to 0.023. These are the bootstrapping graphs showing our confidence interval. The results were very similar between the parametric and the non-parametric methods. Since we had evidence against normality, it would make sense to use the non-parametric methods. But we also had an influential point. We might want to consider removing this point and rerunning the analysis. Both the confidence interval and the hypothesis test give us similar results. We have evidence against the null hypothesis of no linear relationship.